Okay, so what we're going to do now is take a look at parallel transport. It's possibly the idea in differential geometry or manifolds that has the biggest observational impact on stuff we see. All right, all orbits are parallel transported along themselves. All spin vectors that we see for neutron stars or black holes or whatever are parallel transported along the orbit. And so understanding how that works not only gives us an idea of how the other thing evolves, but it also can be a measure of how we experimentally test whether a space-time is curved or not. Okay, because parallel transport is intimately connected with your derivative operator and is intimately connected with curvature. And so to give you an idea of what it is, it's basically the aim of these couple of lectures is to develop an intrinsic idea of what curvature is. And one way we did it, in fact, the way that people originally determined that the Earth was curved and not flat, was basically you take a vector and you parallel transport it along a curve. Okay? And the way we say, just the naive initial way, and this is the thing that actually becomes concrete, the rule for parallel transporting a vector along a curve is you want to keep, or the minimum rule, you want to keep the angle with the tangent of the curve constant. Okay, so for example, if you wanted to parallel transport a vector along this curve C, and you lived in a flat plane, you would say, let's begin over here, okay? I want to transport it this way, but I'm going to keep the angle that I make with a curve constant. So I have a tangent to this curve, and there's an angle there, and I'm going to keep that angle constant. And then I'm going to keep it constant over there, okay? So that's my rule. Then I get to this corner, now I want to transport it along this curve. Then I keep this angle constant, like that, and I keep the angle constant over there, and then I get to the end of that part, and I now want to transport it along this curve, so then I keep this angle with a curve constant, and there I go. If I'm flat, I will go exactly back to the same vector I had. So very easy in flat space, but what happens in curved space, you can do the same thing, have the same rule, and instead of doing this, keeping the tangent the same, going all the way around and coming back down, and coming back to the same vector, if you're on a curved surface, then if you parallel transport the vector with a rule that you are keeping the angle between the tangent of the curve constant, then something else happens. Okay, so have a look at this. Suppose we start with this vector A, and we are on the sphere, we keep the angle between A and this curve constant as we go to the North Pole. So there's the same angle, we get to the North Pole and we point that way. Then we transport it along this curve, we keep this angle constant, which is roughly 90 degrees, and then we get down here to B, and then we again transport it back, but we keep this angle between AB, the curve AB constant, so that angle's constant. We get this vector back, and it is a completely different, pointing in a completely different angle. And the moment this happens, you know that your space-time is in fact curved. And they have done this to verify that the space-time around the Earth is curved. The thing is, you need a vector, okay? And the vector, a very natural vector is they take like a metal cube and they spin it up very, very rapidly. So then you have the vector that tends to want to stay like that. They put it in orbit around the Earth for thousands and thousands of times, and then in the end they measure whether the vector has changed or not. Okay.
So it's the same idea if you want to test GR.
It is exactly, in fact, it is exactly that. In fact, if you're in flat space, and you do this with a spinning vector, like even a bicycle wheel, you take it around a closed curve and there's no friction, you'll come back pointing exactly the same way. If you lived and around a black hole it would point somewhere different. So it is actually transporting a very clear vector like that around a closed curve and observing the difference is a direct measure of whether your space-time is curved or not. Whether the curvature is due to matter or something else. The moment you take a vector, you put it around a closed curve, and it doesn't come back onto itself, you're in a curved space-time. Okay. So one thing over here is parallel transports needs more than just the structure of the manifold. Up until now, we've said a manifold is a set of points that has this map, the charts from the manifold to the real part, and we had the rule wherever you had an overlap of two different charts, they had to be consistent, and we found the overlap function, and that was the conditions on our manifold, right? And then we went and said, okay, we can have linear maps on the manifold defined at a point. Those are tensors, and we had certain operations like exterior product combining the two and contraction, like basically summing over the tensors, that we could do. So that's all to do with the manifold structure. Now to get parallel transport to work, we need a little bit more. And it's going to turn out we're going to build up the structure that we require to actually describe parallel transport in any sphere systematically. So once again, it's closely associated with the idea of a derivative operator. That's to be expected because remember our vectors were associated with directional derivatives. Okay. But this derivative operator, we actually are going to look for one that's not dependent on the charts. Remember, whenever we worked with vectors, we always said we have a vector, its associated directional derivative. To get a basis for the vector, we needed a specific chart. Okay, we're now going to start transitioning to derivative operators that don't require a specific chart. Okay, and a vector in manifolds is once again said to be parallel transported if its derivative along a curve is 0. Okay, so this idea that your tangent point or this angle doesn't change is simply saying that the component of the vector along the actual curve is unchanging. Okay. The mismatch of parallel transported vectors on curved surfaces indicate that successive differentiations don't commute. Okay, so this is just an idea I'm throwing out there. I will prove it to you later on. Right, when we worked in flat space, we always said like if you take the derivatives in the one direction and you take derivatives with respect to y, if you switch the order, you'll get the same answer. In curved spaces, this is no longer true, and it is directly observed because your vectors don't close. Okay, so the two ideas that you have a mismatch in parallel transported vectors and derivatives that don't commute are both indicative that you're in a curved manifold. Okay, and now an important thing is, given a metric, we had an idea of an inner product, right? We used the metric to contract an up index and a down index quantity. Okay, we could use a metric to transform a one form into a vector or a contravariant vector into a covariant vector. Important, parallel transport doesn't actually require that you have a metric. You can define parallel transport just with the stuff we have with a manifold without saying that you have a metric. So remember, we defined what the metric was just to get a feel for it. We said it was a symmetric tensor. It was not degenerate. In other words, you could find its inverse, and it had some other properties that we got earlier on. You do not need a metric to define parallel transport. However, if you do have a metric, it becomes easier. It's a subset, let's say, a subset of all manifolds on which you can define parallel transport has a metric. So parallel transport doesn't require a metric, but it does require derivative operators. Okay, and in fact, it is more general than an inner product associated with a metric. The only reason we introduced the metric is because it's easier, and it's an example of a two-tensor that has certain special properties. Okay, so what I'm going to do now is I'm going to define the most general derivative operator on a manifold. And then I'm going to give examples of it, and then I'm going to give a way of computing derivatives that are not dependent on the coordinates you're actually working in. And this is where it becomes exceedingly powerful, and where the applications are in GR, but whenever you work with curved coordinates. Okay, so the covariant derivative operator, and we often denote it like this, okay, a nabla, on manifold M is an entity, okay, it's a map that takes a smooth tensor field. So it's now we're going to find a derivative operator not only for functions but for any tensor field. Okay, it takes the smooth tensor field, and let's represent our smooth tensor field as a KL tensor. In other words, K up indexes, K and L lower indexes. It takes a smooth tensor field to a smooth tensor field. Okay, and we're going to note that one, we have an extra down index with once again K up indexes and L lower indexes. So therefore this whole entity is an example of a KL plus 1 tensor. Okay, so just like the gradient of a scalar transforms a 0, 0 tensor into a 0, 1 tensor, so a derivative operator in general transforms a KL tensor into a KL plus 1 tensor. Okay, and these are the minimum properties it has to satisfy in order to be a derivative operator. Okay, so the first thing is it's got to be linear. Okay, in other words, if you have two tensors A and B of the same type, and you have alpha and beta in R, then the covariant derivative operator applied to the linear combination of those tensors is just, okay, and A and B are now constant, is just the alpha times the derivative operator applied to the first tensor plus beta times the derivative operator applied to the second tensor. Okay. The second thing we need is Leibniz's rule, and that is if you have any tensor, KL tensor, and any other tensor B, which is L, K prime, L prime, so different type of tensor, and you look at their product. So remember, the exterior product is just the exterior product of the components. And you want to work out the derivative of this product, then once again, just like the product rule that we've studied in calculus from the start, it's a derivative operator applied to the first tensor times the second tensor plus the A times the derivative operator applied to B. So it's simply the Leibniz's rule works for any tensor. Okay, and then the third property is it commutes with contraction. And what that means is, suppose you have like a tensor where you've contracted two indexes. You can first take the derivative of the contraction, or you can first do the contraction and then take the derivative. It doesn't make a difference. Okay, so what you have for any A in a KL tensor, you're going to have that the derivative operator applied to A, where you have a contraction other to its two repeated indexes, is simply going to be the derivative operator applied to the thing, and then you can contract afterwards. So contract, the order does not make a difference. Right, here in this example with the brackets, you've contracted it first and gotten a K minus 1, L minus 1 tensor. And over here you apply it directly and then you contract it afterwards. The result is exactly the same. Okay, and then the next condition is there must be consistency with viewing tangent vectors as directional derivatives. So remember we defined our tangent vector as a series of directional derivatives on a scalar field. And we want this derivative operator to do the same thing. And the way we write that down is for all functions that map the manifold to the real values, remember we had a tangent vector was an element of the vector space, and we can now if we define our directional derivative operator so that we can write our tangent vector as TA times the covariant derivative operator applied to F. Okay. In other words, the covariant derivative operator behaves the same as the normal derivatives of F. Okay. And then the final hypothesis is that it must be torsion free. In other words, if you have a scalar function that maps the manifold to the reals, the order of differentiation with a covariant derivative operator for a scalar function, and note this is only for a scalar function, must commute. Okay, so the idea that if you have a function on your manifold, the order of differentiation doesn't matter, that is there. Okay, so those are the only 5 hypotheses you need to actually define your covariant derivative operator in general. And you basically, everything that we know about covariant derivative operators, we basically derive from using those 5 definitions. Okay, so the conditions 4, 5, and 2 basically give a very simple expression for a commutator. Remember, we worked out, we had a vector field that we operated. If you operated it on a second vector field and then switched the order, we defined that to be our commutator. Okay, we can actually now use 4, 5, and 2 to actually give an expression of the commutator in terms of the derivative operator. So, for example, suppose you have 2 vector fields, and it also just is an example basically of how to use the derivative operator. Suppose you have 2 vector fields, VA and VB, right? And remember, they always work on, they map the set of all functions to R. Okay? They're basically the function interrogator, if you remember the earlier lecture. So then, suppose you have 2 vector fields, and you now wanted to express them in terms of your derivative operator applied to any F. The way you would do that is, remember we had the commutator, which was simply V applied to W applied to F minus W applied to V applied to F. And so what you can now do is, remember we have this condition 4, that a vector T applied to F is simply the components times the gradient applied to F. Okay, and so we simply, for W applied to F, we simply work out the components W times the gradient operator applied to F. And the same over here, the components of V times the gradient or contracted with the gradient operator applied to F. And then when we want to apply V to the bracket, it's again the vector V's components times the gradient operator applied to the bracket. And once again, when we want to apply W over there, we have the vector, the components W of A times the gradient operator applied to this thing. And so what we do now is we can use the fact that we have numbered what's basically Leibniz's rule to expand this thing. Okay, so what we have over here is we can first say this first term is VA times the gradient of A applied to WB, so that's that term, times the gradient of F. Okay, so that's the first component. Then we're going to have another component which is simply VA, VB plus this operator, the gradient of A applied to the gradient B applied to F. Okay, that I haven't written down yet. And then we're going to subtract W of A, once again using Leibniz's rule, the gradient of A applied to VB applied to the gradient of F. So that's that second term. Okay. But the part that I left out is basically WA, VB, the gradient of A applied to the gradient of B of F. But because we have these two there and there's a minus sign there, they cancel. And all you're left with is the spot. Okay, so the commutator of the components of the commutator of two vectors is simply the vector applied to the the vector contracted with a gradient of the other vector minus the other vector contracted with a gradient of the first vector. Okay, and remember when we worked out this derivative, the commutator, we had this very long calculation on the board over there, and all the second derivatives cancelled. Okay, and those things were cancelling simply because this is true. Okay, so you always, whenever you work out a commutator, you always end up with components that only contain one derivative, even though you are effectively applying two vectors to a function. The difference, if you switch the order, will only result in one derivative. Okay, so this is just an example of how to actually use these definitions that we've got over here with our covariant derivative operator to actually get something useful out. Okay, so we now have this abstract thing. We call it an operator. We've given it a little triangle name. The only thing it has to do is obey these rules. Okay, and we said if we can find it, we can already write other things in terms of it, but we haven't yet proven that we can always find it. So mathematicians are obsessed with existence, and what you can do is you can prove that at least one of these operators exist. Okay, so what I'm now going to do is I'm basically going to show there exist differential operators, and the way I'm going to do it is just to construct one. Okay, so the most simplest differential operator can be constructed in the following way. So, and they call it the ordinary derivative operator, and I just denoted dA. Okay, and what the ordinary derivative operator is let psi be a chart, and then remember the basis of the tangent space is just ddx of mu, which is all the coordinates, and the basis of the cotangent space is simply dx. And remember that if you apply dx of mu to ddx of mu, you get the delta function. Okay, so we have our chart, we have our associated coordinate basis, and if we have any smooth tensor, we're going to say, okay, let me make another smooth, another set of tensors, and the way I make it is I simply take the components of my tensor and on the coordinate basis, and I work out their derivative. Okay, so the most naive way is simply I take the tensor, which is got my aptex index notation over here. To work out the derivative operator, I take the components on my coordinate basis, and I just work out the derivative of every single component, and I say I have a new tensor. Okay? And that I can always do, right? I always can take a set of functions, I can take their derivatives with respect to every single coordinate I have, and then I basically have a tensor, and its components are basically these derivatives. Okay? And what I can show, and it's on a specific coordinate basis, and I can show that that thing actually satisfies all the axioms I've just given. Okay, so all 5 conditions on the previous slide hold for dA, right? The linearity follows simply because an ordinary derivative is linear. Leibniz's rule follows because an ordinary derivative, a product of 2 functions, obeys Leibniz's rule. The fact that scalars commute also follows. The fact that it's consistent with your tangent vector field follows because that's the way we defined the tangent vector field initially, or we proved it to exist. So basically, this derivative operator satisfies all the previous things. The problem is, okay, and in fact, that condition 5 where the thing commutes, in other words, if you take derivatives with respect to dA and dB, then it's always equals to minus dB and dA. So that holds for all tensor fields but not all scalar fields. But there is a reason why we required it only for all scalar fields, is because if you define something this way, the problem is the moment you go to a different chart, you have a completely different entity. Okay? And also, if you go to a different chart, your actual tensor doesn't transform, its components doesn't transform using the nice component transformation rule. So even though we now have an ordinary derivative operator that satisfies the other axioms, it doesn't behave nicely. Okay, so given psi, we can define a derivative operator. So this ordinary derivative operator is basically dependent on the chart you've chosen. Okay, but the problem is the moment you have a different chart, you're going to have a different derivative operator. And that we don't want. We want something that doesn't depend on the operator or the chart we've chosen. Okay, and what's also going to be true is the components in the new chart are not equal to the partial derivatives in the old chart or the prime chart. So you can't just work out the derivative operator in this chart and then transform them into a new chart and then think that it's going to be this related to the new derivative operator. It just doesn't work. So even though we have something that obeys all the axioms, we are clearly still missing something. Okay. So what we basically get is our ordinary derivative operator is dependent on the chart and is not therefore associated with the structure of the manifold. So even though we can write it down, it doesn't capture something intrinsic of our manifold, and we actually want a derivative operator that does that. And so what we're going to do is find out how unique. We've got one that exists. How unique is this chart, this derivative operator? In other words, how many derivative operators are there? And can we actually use what we know about that to actually define the special operator that doesn't depend on our charts? And this is actually how they went and discovered, well, the covariant derivative operator. Okay, so we've got existence, but the operator is not all we hoped for, simply by an example. Uniqueness, let's now have a look. Okay, so C4 is basically, whoopsie, this thing. Okay, so our condition 4, remember, is the idea that we view tangent vectors as directional derivatives of scalar fields. Okay, so we're going to use that to explore the uniqueness. Okay, so by C4, we're going to have that if we have two different derivative operators, they've at least got to agree on something. And what they agree on is the action on scalar fields. So two different derivative operators, if you apply them to a scalar field, they've got to give you the same answer. Okay, so we can't just randomly choose something else. Okay, so we know what it does for scalar fields. Now let's go up one step more complicated and see what happens when we differentiate a 0-1 tensor. Okay, so the way we're going to do it is we're going to say, let's apply the one derivative operator to some function times a 0-1 tensor minus some function times a 0-1 tensor. We apply the one derivative operator function times a 0-1 tensor and the other and subtract off the difference of the other derivative applied to the function of a 0-1 tensor. Okay, and so when we do that, we once again have Leibniz's rule, right? We first apply the derivative operator to f. Okay, so there's the tilde a applied to f minus omega b. Okay, and we're going to do the same thing on this side. We're first going to apply the derivative operator to f times wb. Okay, so that we're allowed to do because of Leibniz's rule. And then we're going to apply this derivative operator to the second one multiplied by the scalar. So we have f times this derivative operator applied to WB minus the other derivative operator applied to WB. Okay, and this thing, we know that this part is at least 0 because the derivative operator applied to the scalar and the other derivative operator applied to the scalar must be the same because of our condition 4. Okay, so these two are the same, therefore they subtract, so we're only left with this thing. Okay, so this is basically an identity that I'm going to use later on. Okay, so you have two different derivative operators applied to basically a function times a 0-1 tensor, and it's simply the function times the two different derivative operators applied to the 0-1 tensor. Okay, so now what I'm going to do is just remind you again of all the conditions just in compact form because we're going to use them. Okay, so remember our covariant derivative operator increases the lower index by 1. Okay, it has this linearity property when you prove things. It has the Leibniz's rule in general. It has the fact that the contraction commutes with the operation. It has the fact that if you apply it to a scalar field, it behaves exactly the same way for all, like the directional derivative that we define the basis with. And we have that if you once again apply it to a scalar field, then the two derivative operators commute. Okay, so those are the 5 things that we're working with. Okay, so we're back to uniqueness. So this is what I used the last time. This is what we were doing with this WB tensor, and we basically showed that this thing is true. What the first theorem that is actually becomes important now is basically when studying the difference of two derivative operators applied to a 0-1 tensor, okay, is what we're going to show is that this thing depends only on the value of omega b at a particular point. Okay? Not on what it does off the point. So typically, you view derivative operators as something that takes you from a point to somewhere else, right? Just because usually if you take a derivative of a function, right, if the derivative operator will tell you how the function is changing off of a point. Okay, so this proposition is unusual. If you make this combination, this difference of two derivative operators applied to a 0-1 tensor, I'm now saying it depends only at the point. Okay, which is weird. And the way we prove that is suppose we have one 0-1 tensor that is equals to another one at that particular point. Okay, and the other one is arbitrary everywhere away from the point. If we can replace B with WB prime, then it clearly doesn't depend on anything other than the fact that than the operator at the point. Okay, if we can replace W with WB prime and get the same answer, then this proposition is true. In other words, this combination where we subtract the two derivative operators applied to a 0-1 tensor, then it depends only on what the tensor was at the point, not how it changes off of it. Okay, and the trick now is, it's a bit finicky. Let us express the difference of these two tensors, of these two 0-1 tensors as a sum of functions multiplied by mu b, okay, where these functions are smooth functions that vanish at p, okay, and mu b are smooth vector fields. So what we're doing here is simply saying, we're expressing the fact that WB and WB prime are the same at p, okay, and they can differ. They are some arbitrary other difference away from p. And what we're now going to do is now apply our two different operators to these two, to the difference of these two vectors, or sorry, 0, 1 forms. And the way we do that is we simply apply the gradient to the sum and apply the gradient to the same sum. So we simply write out this definition of W prime B minus WB in here. We then go and we put the gradient operator inside because the sum is finite. Okay? And we use Leibniz's rule because these guys are smooth functions and these are just 0, 1 tensors. Okay? And in fact, what we do is we make use of this thing that I proved earlier, that we have that this difference is simply f times only the operator applied to the tensors, to the vector fields themselves. Okay, so I've literally, to go from this step to this step, I've simply used that thing I proved earlier. Okay, and what this thing is that because f vanishes at the point, this thing is in fact 0. It's very finicky, but it's also very clever. Okay. Right. Do you at least agree that the difference of these two derivative operators apply to W prime minus B and W prime minus B is equals to 0? Huh? No.
Can you elaborate further?
Can I elaborate further? It's simply using the definitions that I've put in. Okay. Do you agree with this point?
Yes.
Okay. Right. So then the proposition I want to prove is that this entity over here is dependent only on the value of this thing at the point P. Okay, not how the thing is changing off of point P. That's what I want to prove. That's the important thing. Okay. And the way I do that is suppose I have another basically vector field. Okay, that's different from the original one. And I say that if I can replace this vector field with a new one in the equations, then it doesn't. Then proposition 1 is true. Okay, because if the same thing holds for two vector fields that are completely different, except for the fact that they agree at P, then it doesn't depend on what the vector field changed or off of P. Okay, so then I say, okay, I can then go express for any two vector fields that are equals to each other at a specific point, but change away from it. I can express it as functions that vanish at P, but are different, but have that multiply some random set of vectors that are smooth. Okay, and those vectors are arbitrary. So I say, okay, fine, I can express this difference like this. And then what I go is I simply go and I apply these two different operators to the difference, and then I use the fact, and I then write down the way I've expressed the difference. Okay, and I switch the order of summation with the derivative operator. And then what I do is I use this fact that I proved earlier simply by using Leibniz's rule on F times WB, that this entity is equals to that. And then I say because F of A vanishes at point P, the whole thing is 0. Okay, so and so what that effectively does is it proves that I replace B with B prime. The thing doesn't depend on the actual one form away from P, and it's only this, and so I basically prove proposition 1. And what that tells us, Okay, and that, and it's just once again writing out this thing over here, if I write it out, and I collect everything with the primes on the one side and everything with the WBs on the other side, those things are equal. So I can basically replace WB with WB prime, and I get the same result. Okay, so here is the thing. The moment you have this, you have that the difference between two derivative operators defines a linear map of W. Okay. Rather than a dual vector, rather than dual vector fields in the neighborhood of P. In other words, because the thing doesn't depend on what W looks like away from P, this difference of the two operators is actually a linear map. And that argumentation actually leads to a new entity that they're going to call a crystal full simple. It's a way that you actually track how derivative operators differ from each other. Okay? And that eventually becomes a very powerful way of writing down what covariant derivative operators are. In other words, derivative operators that behave like tensors. So it's almost a finicky observation that this difference of derivative operators applied to a 0-1 tensor only depends on the point and not how the vector fields change around it. That actually leads to reasonably profound insight. So let's see how we do it. Okay, so this change in derivative operators defines a tensor that looks like this, okay? And that literally, even if you don't fully track the insight, know that there is a very straightforward, solid argument that actually leads to the existence of this entity. This entity didn't randomly jump out, because many of the textbooks tell you define the Stoffel symbols that do this. They didn't randomly jump out from nowhere. They jumped out from that argument that we've just had. Okay, so this change in two derivative operators basically defines a tensor that basically is a a 1-2 tensor at a specific point. So once again, we're not moving off of the point. We're defining this tensor at a specific point. And what it does is basically, if you're given two derivative operators, delta tilde A and A, okay, you're basically going to have this tensor field such that if you work out the change in the two derivative operators, it's simply a linear map of C. So what we did in the previous slide is we proved that the change in the two derivative operators depended only on the point C. The moment you have that, you can express their difference in terms of a tensor applied to the point WC. Okay, so very important, this entity depends only, is a tensor in the truest sense, that it only depends it only needs to be defined at a specific point. Okay, and once you have this thing, it has certain symmetry properties that is inherited directly from the way you defined it. So let's look at this. Let's say in the simple case where we have WB equals to the gradient of F, okay, and that's also equals to the gradient with the other derivative operator of F. So these two are the same by one of our by property C4, and we can define a 0-1 tensor to be either one or the other. Not all 0-1 tensors can be written in this way, but if you write something like this, you always have a 0-1 tensor. Then you can work out the gradient operator applied to this WB, and the other gradient operator applied to this the same thing, and then using what we've just derived, you see that their difference is CAB multiplied by the gradient of F. Okay, but you also know from property 5 that this gradient, basically you have a tensor equation for this in terms of f, and for that thing in terms of f, okay? And because these things are symmetric, right? This one is symmetric and that is symmetric from property 5, this tensor over here is also going to be symmetric in A and B, okay? So you have that this new tensor that we have, it already has, we know something about it, and we know that if we switch these two indexes at the bottom, they are the same. Okay, and so just before I go, well, I'm going to stop here, I'm not going to go on, is this, I'm going to tell you a little bit about this thing. So this thing is something that when we work with a metric, we call the Christoffel symbols. What this thing is actually doing, in a way, a very abstract way of thinking about it, is it's storing the way your basis vectors change when you take derivative operators. Remember when we worked on a Cartesian basis and in a spherical basis? In a Cartesian basis, when we had a vector, when we took a derivative of the vector components, we could just take a derivative of the components themselves. In the spherical basis, that very first example, or one of the first examples we did, if you write down the components of the, on a spherical basis, and then you want to take a derivative of the vector, remember you had to take the derivative of the components, but then you also had to work out how the basis vectors change. Okay, what this thing does, the C, is it actually gives you eventually gives you a systematic way of storing how your basis vectors are changing. Okay, and that is why it's just, this is not as precise as these definitions, but it does give you an intuitive feel of what it's actually doing. It basically tracks how your basis vectors are changing, and that is why it depends only on the thing at the particular point, right? It doesn't depend on how the function is changing off of the point, because how the basis vectors are changing at that point is actually a function of the point itself. So all our coordinate nastiness, we are eventually going to store in these entities, and they make it systematic to work with every single coordinate system. And what I would recommend is go back, see the assumptions that went in there, and know that it was actually started exactly those 5 assumptions that you have for a derivative operator in general lead directly to the fact that if you apply 2 different operators to one of these things, that it depends only on the point. And the moment it depends only on the point, you can say you can write it as a tensor. And that tensor is actually going to keep track for us of how these basis vectors change in a very systematic way. So it's a complicated step to define this thing, but once you've got it, it becomes very powerful. And it's a very rigorously obtained. Well, the first time I saw these Christoffel symbols, I thought somebody had plucked them out of the sky and they landed there. They're not. There is a very good reason for them to exist. And they come exactly from our definitions of a derivative operator in a manifold. See you tomorrow.